Okay, everybody, we're going to go ahead and kind of continue our look at sequences and series and talk about what types of things can happen. And we were looking at that yesterday in 12.3, but now we're going to put a more, I guess, specific name onto the different type of series that you can have depending on what the terms do. So they're called convergent and divergent. So the actual concept of what those are really isn't too bad. We have just a real basic thing about what each of those mean. Convergent, if something converges, think about what that word means. So if roads converge or things converge, it means they come together. So basically what convergent means is that series has a sum or a limit. So for convergent, it has a limit. The series has a sum. And for divergent, it means it does not. So it does not have a limit. So if you just think about the basic ideas of converge comes together, has a limit, the limit exists. Diverge, it doesn't. That series does not have a sum, does not have a limit. The terms keep getting further and further apart. Grow without bound or go back and forth. So those are the two terms that we're going to be working with today, looking at series and deciding, do they converge, do they have a limit or a sum, or do they diverge? They don't. All right, well, there's some that we certainly know one way or the other, just because of what we know about them. So let's talk about the series that we've done already. So geometric, it really depends on the ratio, right? So think about what kinds of series that are geometric converge or would have a limit. Those would be the ones where the terms approach that asymptote, approach that y or x-axis. So for the ones that have a ratio that's less than 1, those are going to converge. And I'm saying absolute value because they can be positive or negative. Remember, in geometric, they can bounce back and forth, but they could still approach 0. If the ratio is bigger than 1, so 2, 3, times by 2, times by 3, think about what those exponential kinds of equations would do. They would continue to grow and grow and grow. The values get bigger and bigger. Those would definitely diverge because those would be continuing to get bigger. They wouldn't have a sum. They wouldn't have a limit. So powers, anything like that, those will grow exponentially. All right, how about arithmetic? Think about what arithmetic does. Remember, geometric is like exponential, so you can think about what those look like. How about arithmetic? What are those like? Linear. All right, so think about what lines do. So lines continue to grow and grow and grow and grow, constant rate of change, not as fast, but they continue to grow, or keep getting smaller and smaller and smaller and smaller and smaller if they have a negative slope. Well, they're never going to approach a limit then. You're always going to find a term that's bigger, the next one and the next one. They continue to grow and grow and grow, so those will always diverge. By definition, arithmetic series always diverge. So if you know something is arithmetic, that's really your reason. Those terms just continue to get bigger, 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 or smaller. And that would be things like any sort of thing that can be written with a slope or a constant rate of change. For everything else, what we really have to do is look at the nth term. We really have to see what's happening as those terms get bigger. Are they approaching something? Do they have a sum? So they have a limit, so the limit exists, then they would converge. If they do not, then they diverge. So there's things that we can look for, though, in these nth term. We write that rule. So there's some things that are kind of common that we'll see. One thing is factorials. So we'll see a lot of numbers like that. So factorials, that's the exclamation point. So 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. Oops, 120, dot, dot, dot. And other things, perfect squares, perfect cubes, things like that. So squares, cubes, all those kind of lists that might be helpful to look at. So like an n squared or an n cubed kind of rule. So perfect squares, we know 1, 4, 9, 16, etc. Perfect cubes, 1 cube, 2 cube, 3 cube. Those might be terms that we can recognize and be able to write that nth term formula a little bit easier. So you know from doing those limits things, the nth term part is the tricky part, being able to come up with what is that rule and be able to see if the limit exists or not. Okay, so let's try some and just see how that works for you. So for the first ones, it says just determine whether the geometric series converges or diverges. Well, it's super nice if you know it's geometric because then we just have to look at the ratio. If the ratio is bigger than 1, divergent, because those terms would continue to get bigger. If it's less than 1, it'd be convergent. So for the first one, see if you can figure out the r. Remember, if you don't remember what the r is, take any term, divided by the term in front of it, and you can figure out what that ratio would be. So I'll just do the first one. So 1 divided by 10, the ratio is 1/10. In other words, you're multiplying by a tenth each time. If you'd rather have as a decimal, you sure could do that too. So that ratio, 1/10, is most definitely less than 1. So what does that mean? The series converges because those terms will continue to get smaller and smaller, and it'll have a sum. So we would be able to sum up that infinite series, because notice it's dot, dot, dot. It keeps going. So we'd be able to find a sum because it has a limit. All right, how about the next one, though? We know it's geometric. What is your R? So again, if you're not sure, take any term divided by the term in front. They told us it was geometric, so we know that's always true. The ratio is 3. Those terms are going to continue to get huge. They're going to get bigger and bigger and bigger. So that ratio is definitely bigger than 1. What does that mean? It means this one is going to diverge, or diverges, is divergent. Hey, that's a movie and a book. So when we look at diverging, what that means is it doesn't have a sum and it will not converge on anything. So diverges, there's no sum. No sum exists. No limit exists, so we can't have a sum. So for geometric, it's not too bad. All right, let's take a look at something that isn't geometric. We're going to talk about sort of a whole bunch of different examples now. What is it? What's going to happen? So limits existing means that it would have a convergent, has a sum, converges. Limits not existing means it doesn't. So if the limit exists, convergent, limit doesn't exist, divergent. So let's see if this limit exists. What happens to sine as x gets bigger and bigger? Well, the values for sine, when you think about the function for sine, hopefully you remember what the graph looks like. All right, starts at 0, up to 1, down to 0, down to -1, back to 0, and it continues through that cycle forever and ever. The range for sine then is between -1 and 1. So that numerator is always going to be a number between -1 and 1. What's the bottom going to do? Well, as x continues to get bigger, the bottom is going to grow without bound. So it's going to get huge. So you're going to have a number between 1 and -1 divided by something that gets massive. So that is going to be a situation where the bottom grows, the entire thing is going to go towards 0. So it has a limit. So because it has a limit, so as we would say, the limit exists. So what does that mean? Well, if the limit exists, that means it is convergent. Or it converges, however you want to say that. So if you can find the limit, that's looking at that AN statement, the rule. How do we generate it? So think of this as like the rule. This is your nth term. So it's the AN formula. I guess I'll write it that way. So the AN formula, the rule that describes the terms in that sequence. So we call that the nth term formula. That's another way to say it. So if we can look at that and see if the limit exists, then we'll know for sure whether it's convergent or divergent. All right, so let's take it one. Instead of them actually giving us the formula, they just gave us the series. So the last one, they kind of gave it to us already. What we have to do for this one is see if the limit exists or not. Well, let's take a look. If it's convergent or divergent, let's check the usual suspects first. So if it's arithmetic or geometric, we know by definition. So let's peek. Let's see. What are they doing each time? I'm going to write this first one as a 1 over 1. All right, so to go from one term to the next, let's see if you can figure it out. Is this one geometric? Kind of looks like it is. What are they multiplying by each time? And you say to yourself, 1/3. All right, so what does that mean? If it's 1/3, that means the ratio is less than 1. So if the ratio is less than 1, that means the limit exists. And by definition, because it is geometric and the ratio is less than 1, we know that this converges. So again, if they give us just numbers to look at, we should be able to know. Now, they may not say in the question, hey, this is geometric. So you'll have to figure that out. You'll have to look and see, is it one of those usual things? So because it's geometric with a ratio less than 1, that means the limit exists. So that means it converges. All right, let's take a look at this one. Gets a lot more complicated. This is not just geometric, but there's definitely a pattern going on in the numbers if we can look at it. So I'm going to write the first one as a fraction as well. For this one, I think our best bet, since I'm looking at it, I know it's not geometric or arithmetic, we're going to write the nth term formula. We're going to write that limit statement and see if the limit exists. If the limit exists, we know it converges. So the limit as n approaches infinity of. We're going to go ahead and write in this little bubble here what the formula is for the nth term. And we're going to see what that's equal to. Is it approaching something? Does it have a limit? Convergent. If it doesn't, divergent. So what's going on the top? Well, it looks like we have powers of 3. So that would be 3 to the first, 3 to the second, 3 to the fourth, 3 to the third, 3 to the fourth, 3 to the n. And on the bottom, so you can do these tops and bottoms separately. You don't have to try to come up with one rule. Kind of separate those fractions out. 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4. That's factorial. So n factorial. So now the question is, which grows faster, the top or the bottom, because that's going to determine whether it doesn't exist or it goes to zero. So which grows faster? That's always going to be your question that you're looking for in limits. Well, we talked about for each of these before, hopefully when we went through 12.3, the fastest growing thing is always factorial because you're multiplying by a bigger number. On the top, you're always just timesing by a 3 each time. On the bottom, you're going to times by 4, and then by 5 and 6, and then 10 million and 20 million. The bottom is going to get huge. The top is going to grow too, but not as fast. So because the bottom grows faster, that means it goes to 0. So what does that mean? The limit exists. So if the limit exists, that means it's convergent. So if that had been flipped around, if the 3 to the n had been on the bottom and the n factorial had been on the top, then it would be divergent. It would not have existed because those terms would continue to grow. Okay, we're just going to try a few more here and make sure we're on track for examples. All right, so take a look at the next one. Your whole goal, if you don't know exactly what it is for sure, is to try to figure out the rule for it. So this one, I don't think it's straight arithmetic or geometric. We could definitely check the top and the bottom there. So I think we're going to have to go ahead and write the limit statement here. The limit as n approaches infinity. Again, I'm going to be filling in this bubble for whatever the nth term is. And we're going to check and see if that limit exists or not. All right, since it's fractions again, I'm going to try to split it up. If you look at the top, just the top by itself, how do you go from one term to the next? Well, it looks like you're timesing by 2, right? You're doubling. So that is exponential. So you can think of that using your AN formula if you want, because on the top, just this set of numbers right here, that's geometric. Your R is 2, right? You're multiplying by 2. You know A1 is 2. And you could use the geometric AN formula if you wanted to, right, to come up with that expression. So I'll try it that way. So the nth term would be A1, which is 2. The ratio is 2 to the n minus 1. That would be your nth term formula. Well, and that's great. That works awesome. And you can put that right in the top. But some people just look at it and say, hey, this is term number 1. That's term number 2, 3, and 4. The first term is 2 to the first. The second term is 2 to the second. The third one's 2 to the third, 2 to the fourth. Can I just say 2 to the n? And the answer is absolutely. That's just powers of 2. That's all that is. And if you look over here and simplify a little bit further, that's 2 to the first, right? And 2 to the n minus 1, if you add your exponents together, you end up with 2 to the n. It's exactly the same thing. So what's ever easier for you? If you recognize part of your rule is either arithmetic or geometric, you have a formula for that, you can use it. But if you can just come up with something, great. Okay, look at the bottom. Just by itself, let's see if we can figure out what's going on with this. So on the bottom, it looks like we're going up by 3, then by 5, then by 7. So it's not arithmetic. It's going up by more each time. So I'm going to try to match it with some of the other numbers that I've done. This looks suspiciously close to the perfect squares. First perfect square is 1. The next perfect square is 4, then 9, then 16. So how do those numbers on the bottom relate? Well, they're all 1 bigger. So that would be the perfect squares plus 1. Okay, so that one's a little trickier to figure out. You have to look at the top and the bottom separately to decide what's going on. All right, so what does this all mean? So once we get our limit statement written, and that is the challenge for most of these, which grows faster? So we have to keep going back to that question. So which grows faster? So we said factorial is definitely, I can't spell, faster. So factorial we know is kind of trumps everything else. That's the fastest growing thing. Then down to our exponentials where you're timesing by something, and then down to all the polynomials. So obviously the bigger the power for a polynomial, like n to the fourth would grow faster than n to the third, all the way down to linear growth, which is kind of the saddest little, slowest growing thing. So let's take a look. So you have a exponential on top, and you have a quadratic on the bottom. So which would grow faster? Well, the top for sure, because that's going to be timesing by 2, doubling each time. So you have faster growth on the top, which means this limit does not exist. It's going to grow faster on the top than it will on the bottom. So the limit does not exist. What that means is it is divergent. So again, if it had been flipped, if that 2 to the n would have been on the bottom, then it would approach 0, and we would have had a situation where it would have converged. Okay, try a couple more here. All right, so let's take a look at this one. Convergent or divergent, we're going to try to come up with the rule. So we're going to write our limit statement. Check and see if it's arithmetic or geometric. I don't think it is. So again, we have a fraction. And we're going to write our rule for the nth term, and we're going to see what it's equal to. All right, when I know everybody can do the rule for the top, so you can feel good about yourself. It's 1. Okay, then on the bottom, 3, 6, 9, those numbers by itself, just those, you're adding 3 each time, right? So that's linear growth. That's regular old AN for arithmetic. But they're all squared. So you can figure out what the rule is just for those bases and just know that that's going to be squared when you do it. So how do we figure out the series for 3, 6, 9? What would that be? Well, that's arithmetic. So A1 plus n minus 1 times d. So if you can't see it, if you just can't come up with a rule, you can always go back to the formula. So the first term is 3. N minus 1, common difference is 3. So 3 plus, distribute, 3n minus 3. Looks like those 3's cancel. So the nth term would be 3n. In other words, it's multiples of 3. Think about that. It probably makes sense. Some people don't even have to do that work with the rule, with the equation. They can just look at it and say, okay, if this is term number 1, and that's term number 2, and that's term number 3, 3 is 3 times 1, 6 is 3 times 2, 9 is 3 times 3, so it's always 3 times n. Whatever way is easiest for you, you go ahead and do that. But if part of your rule is arithmetic or geometric, you have a formula for that. Okay, so let's take a look and see what we have going on here. So we have 1 over something being squared. Well, the bottom is going to grow as n gets really, really big. So that's going to go to 0, which means the limit exists. And because I know the limit exists, that is convergent. Or it converges, however you want to say that. Okay, so look at your rule and you should be able to figure out what our rule is going to be or what it's going to look like. Okay, couple last ones here. So convergent or divergent, take a look at that series. Finally, we don't have a fraction. Let's take a look. Is it arithmetic or geometric? Is it one of those? Well, first one I'm going down to, subtract 2. This one's arithmetic. Like the whole sequence or series itself is arithmetic. What does that tell me? By definition, will that ever approach anything? No, it's going to keep getting smaller and smaller and smaller. It's never going to approach 0. The common difference is -2. By definition, you can say this diverges or is divergent. All arithmetic, no matter what their common difference is, are always divergent. Those would be nice ones to check for. All right, and the last one. Okay, let's take a look and see if you can figure out what this guy is. Okay, doesn't look like you're adding the same thing. Let's double check and see if it's geometric. So see if there's a common ratio. What are you timesing by each time? It looks like a half, huh? So you could take any term divided by the term in front of it, right? And you could still figure that out if you needed to. So we could come up with the 1/2 that way as well. So this one's geometric. Also nice because if it's geometric, you can take a look at the ratio and check and see if it's greater or less than 1. This one's less than 1. What does that mean? It means the limit exists. Because the limit exists, we know that it is convergent. So it really all goes back to, does it have a limit or doesn't it? So if you know it's arithmetic or geometric, golden, because you know something about those series. But if it's not, that's when you have to write the limit statement. Okay, so here is the assignment. It's on page 791. So that's what we'll be working on in class. So you can jot that down. And I will scroll it down here a little bit too so you can see all the way to 38 so you can see all the questions. And we'll talk more about convergent, divergent.